right, so let's go through the quiz. I guess before we do that, just like general stuff. So today we have lab afterwards. We'll be finishing the melting point lab and doing the recrystallization lab. Then next week we have a quiz due on Wednesday again, the one I just gave you. Everybody got a copy of that? And this will be on kind of like the beginning of chapter 3, the stuff that we really talked about today, and maybe a little bit on Monday, but mostly today, so you should be able to do this mostly this weekend. Then next week we will finish chapter 3. We have another lab on Wednesday, and then the week after that's our first exam. So we are getting close. The first exam's a little early because of the Lincoln birthday holiday this year. So, which is good, I think. I think it'll be a little bit less on there than there would be otherwise if it was later, and it'll give you some feedback early on if what you're doing is working or if you need to change up some stuff. So just 2 weeks until the exam. I will grade these quizzes and get them back to you hopefully next week. So let's go through the answers here. So first off, when you went through this quiz, how did it go? Did you find that you had to find a lot of extra help, or were you able to work through it more or less? What do you think?
I need extra help.
Need some help? Yeah? Were you able to find the help that you needed?
Yeah.
Okay. Good. All right. Well, as always, let me know if you're having trouble. You can come see me. I will not give you quiz answers at office hours, but I will certainly help you to work through that and find the right resources and help you through some of the material. So, all right. So what is organic chemistry? Organic chemistry is chemistry based on carbon-containing molecules and some of those other atoms. Whatever you said. There's pretty broad definitions of organic chemistry, so I think that's okay, whatever you said. Which of the following are organic molecules? We would consider this one and this one to be organic molecules, and maybe water if you really make a case for it, because it's involved in organic systems and it's something that we're going to deal with a lot in this class. I think technically by the book's definition, those two are probably the best answers. Definitely sodium sulfate we would say is an inorganic compound. So I'll put a dotted line around water because I would say that is borderline organic compound. All right, covalent bond, ionic bond. This is kind of some general chemistry stuff. Most of this was, as we said, review from general chemistry. So our covalent bond is going to be that shared electrons where the electrons are in both valences at the same time, whereas an ionic bond is simply the attraction of a positive and a negative particle. You don't actually have to have electron transfer for an ionic bond. Like you don't have to have electrons coming from this atom and going to this atom. You just have to have two ions, positive and negative, and they attract each other by electrostatic forces. So for the octet rule, with covalent bonding, we would say that it is that the covalent bonds form so that the individual atoms then have an octet, including the shared electrons. For ionic bonds, they tend to form ions so that they can have an octet in the valence, so 8 or 0 electrons. Electronegativity influences the type of bond because if there's a difference in electronegativity greater than about 0.4, then you have the electrons being pulled more to one side or the other. And then C2H2 looks like this. Okay. And the hybridization of both atoms are sp. They are sp hybridized. And it is not polar. All right, let's take a look at methylamine. So carbon has 4 valence electrons, hydrogen has 1, and nitrogen has, not 3, 5. So that's a total of 10. And so our Lewis structure is going to look like this. And the shape of this molecule around the carbon. Oh, I forgot the carbon. Sorry. Okay, well, that's going to not work. So let's just add this. It's not going to be super neat, but you get the idea. So something like that. And then this is should only have 2 hydrogens on the nitrogen, not 3. And then the shape of this molecule around the carbon would be tetrahedral. And around the nitrogen would be trigonal pyramidal. If you said tetrahedral there, that's okay. Remember that the tetrahedral includes the lone pairs, and that gives you the correct bond angles. But the actual shape of it, physically, because the lone pair doesn't actually like show up in the shape, we call that trigonal pyramidal. So if you remember from general chemistry, you had the basic like overall shapes depending on the electron groups, and then the shapes as you removed or as you replaced atoms with lone pairs, those shapes changed into other things. So we would say that's trigonal pyramidal. However, especially in this class, the most important thing is the bond angles and understanding like the hybridization, things like that. So if you said that that's tetrahedral, I'm okay with that. In general chemistry, that would be wrong because we really care about those names. Here, I think that's okay. So what are the approximate NCH bond angles? They should be about 110 degrees. So this molecule is polar. The carbon and the nitrogen are both sp3 hybridized. There's no formal charges are 0 on carbon, hydrogen, and nitrogen. And methylamine would have 6 sigma bonds and no pi bonds. Any questions about any of those? All right. Okay, this is the one we looked at in class, acetate ion, and so you can kind of go back and check that on your notes from class. So you have the C double bond to O, and then a single bond to the O with the formal charge, and then you show the arrows going back and forth. Now when I grade this, I am going to be pretty specific about making sure your arrows are going the right direction, making sure the lone pairs are in the right place, the formal charges are in the right place. All that kind of bookkeeping, which is really what it is really important for what we do later. So if that's a concern, or if you get the general idea, I'm glad you get the general idea, but it does actually have to be specifically correct in that case. All right, in organic chemistry, what are functional groups? Functional groups are the parts of the molecule that actually do the connecting and disconnecting and participate in the chemistry. However you explain that, I'm sure is fine. And a primary alcohol, we didn't talk about primary, secondary, tertiary groups, I don't think, specifically last week, but that's something you could look up, and that's something we will be talking about. A primary alcohol is anything where the alcohol is connected to a carbon that has at least 2 hydrogens on it. So it's sort of like at the end of the chain. Secondary alcohol is the alcohol coming out kind of in the middle of the chain, and a tertiary alcohol is one where the carbon that has the alcohol on it only has other carbons connected to it. So no hydrogens connected to it. And I believe that's in a table in your book somewhere. And then an aldehyde, so to do that, you look up the functional groups. Ideally, soon, definitely by the first exam, you just know all the functional groups, but for the purposes of the quiz, you would look it up, and an aldehyde molecule is going to have this type of a functional group on it. And then you can add whatever else you want attached to it. So maybe something like that. All right, any questions about any of this stuff from the quiz? All went okay? All right. One thing I am just a little bit worried about in terms of doing these take-home quizzes is that when that exam shows up in a couple weeks, you haven't really had the chance of like sitting down and having to really do it like right then without references or without help. So make sure when you're doing these quizzes, even if the one you turn in is better, it's worth your time to just take a couple minutes and sit down with the quiz and see if you can do it as though it were an exam. Like see what you can do on your own and see what you really need the references for, even if that's not the one you turn in, just so you know for yourself, okay, I understand these things, I don't get this yet, and I need to work on that a little bit more. Make sense? Yeah. Okay. All right, then let's move on. So today I'm really excited because we get to start talking about some real fun organic chemistry stuff. We're done with our review of last year, or 2 years ago, or 10 years ago, or whenever it was that you took general chemistry, and we're on to some actual organic chemistry. So chapter 3 is a big chapter. I don't know if you've worked ahead at all. We're actually going to skip over chapter 2 for now, which is acids and base stuff. We'll get into that when we need it later, but we're going to skip over to chapter 3, and chapter 3 is a big chapter. We'll do some initial stuff with drawing structures and trying to communicate about these organic structures, and then we get into some of the really some of the most difficult stuff of the semester, the visualizing things in 3 dimensions and trying to figure out how to draw and manipulate these fairly complicated shapes. So we're going to take a couple days to do that, actually really almost 3 full days to work through all this stuff. So let's get started. We mentioned last time a little bit about alkanes. So alkanes are, we defined them earlier as carbon and hydrogen containing compounds that don't have any double or triple bonds. Another way we might also say that is carbon-hydrogen compounds where all the carbons are sp3 hybridized. So alkanes are compounds with sp3 carbon. They have the formula CN, H 2N plus 2, which means that however many carbons you have double the number of hydrogens plus 2. So if it's C4, then it's H10. We'll also talk about cycloalkanes, which have a little bit different formula, but let's focus on the alkanes for now. So we're first just going to make a little bit of a table with some of the simpler, shorter alkanes, and then we'll talk about actually what's going on in that table. So we're going to have the the molecular formula the name, what we call the condensed formula, and then what the book calls the line angle formula. Depending on the references, yeah. I don't know. I never know how to answer that question because they're not terribly functional. They don't have much reactivity. They only react with very reactive things. So usually when we talk about functional groups, we talk about functional groups that are attached to alkanes or attached to like the rest of it. I think technically, sure, let's call it a functional group. But we're not going to talk about a lot of like reactions of specifically alkanes. We're going to look at the other functional groups more. So I'm not entirely sure how to answer that question. I think you'd find different answers for it. When we talk about these line angle formulas, these are going to be, this should be new to most of you, but it's also the most important way that we write chemical formulas, and so we're going to make sure that we can do it. Other names that you will find for this are line structure, bond line structure. Sometimes they're called skeletal structures. So if you're looking up other references, videos, or things like that to help you figure this stuff out, or if you're looking in other textbooks, they may not be called line angle formulas, but you'll see they're pretty recognizable. All right, so let's start from the beginning, from the little one, which is CH4, the smallest alkane. Does anybody know what that molecule is called? I think I heard it. Yeah, methane. Right, and its condensed formula is just CH4, and it doesn't have a line angle formula because it's so small. So that's all we'll say about methane. All right, let's go on to the next one. So if we add another carbon and we have C2, how many hydrogens is that going to have? 6, right? Because 2 times 2 plus 2 is 6. So it's going to be C2H6. This one's called ethane. The condensed formula, which we talked about a little bit last week, is where we show all the carbons, but we condense the hydrogens onto them so that we're not drawing a line for every single hydrogen, which is going to be really important as our structures get bigger and bigger. So the condensed formula for ethane is going to look like this. So 2 carbons in a row with hydrogens, 3 hydrogens coming off of each carbon. So to bring that back to last week, the Lewis structure for this might look like this. Just do it on the board because I don't have room on my table there. But this is what we're saying when we say CH3, CH3. Okay? And then our line angle formula looks like a straight line. And we'll talk about why that is in a little bit. But let's get a few more members of our table here first. So then next we have C3H6, H8. That is propane. The condensed formula of propane is going to be CH3, CH2, CH3. And the line angle formula looks like this. Kind of like 2/3 of a triangle. All right, let's try something fun. See if you can fill in the 4th row without me telling you. And I will tell you that it's called butane. But see if you can find the formula, the condensed formula, and the line angle formula by just following the pattern that you see up there. All right, everybody try it? Okay. So the formula should be C4H10. Yeah? Yeah? Nice. Good job. The condensed formula is CH3, CH2, CH2, CH3. Yeah? Nice. And then our line angle formula is going to look like that. Anybody get that one? Wow, nice. Good job. Okay, so now we've got a few on here. Yeah, question, Nicole. What do you mean? So yes, it does, because let's look at what that would look like. That's a good question. So if we had CH3, CH2, CH3, CH2, then we're saying CH3, CH2, right? Two hydrogens on that carbon. CH3, and then somehow we have to connect our last CH2. You see the problem here? So that carbon's now going to have too many bonds, 5 bonds, and that one's not going to have enough bonds. Yeah. So our condensed formula tells us the specific order that we're going to connect this in, whereas a molecular formula, you can kind of put things anywhere. All right. Yes?
So with the line angle formula,
Yes.
would then also be wrong if it was like a little triangle and then a straight line?
Not really, not quite, and we'll get to why that is in a second. Yeah, that one's okay, but not great. Like it's acceptable, but this is better. Any other questions before we get into it? Okay, so let's talk about what's going on here with these line angle formulas. So what are your guesses? How do we make line angle formulas? What's going on with that zigzag line there? What does it mean? Yeah, please.
It's just the carbon to the carbon, but it's also showing the bond angle for the carbons.
Yeah, so in this structure, we've basically abbreviated writing carbons and hydrogens. So in a line angle formula, the ends of lines and the points at which they come together indicate carbon atoms. So if we were to number these carbons just to keep track of everything, 1, 2, 3, 4, then we could similarly number the carbons on our line angle formula like this. Whoa. 1, 2, 3, 4. So each end of the line and then each part where they zig or zag is a carbon. So the reason that it zigzags is, one, because it better represents what the actual bond angle would be, because those zigzags are going to be about 110 degrees. But also, if it was straight, we'd have no idea where the carbons were. So the zigzag allows us to see where those carbons would be. Now to Jasmine's question, there's other ways that you could draw this, and that we would draw this depending on what's going on. This is what I would call maybe like the stretched out form. But we could draw it something like this. That still maintains the same bond angles, the correct bond angles, but it goes kind of down instead of out. We could do that on the other side. We could kind of like flip it over and do it more like that. Those would all be okay. But the idea is to maintain those bond angles when you can. So what about the hydrogens? How can we just not show the hydrogens on those line structures? Why is that okay? Like look at carbon number 2 in our line angle formula. How do we know that that's a CH2 if we don't show anything about there being 2 hydrogens there? Any ideas? Yeah.
Just like hydrogens are assumed to be there in any other molecule, like if you had an oxygen plant, you would have to draw the oxygen on there, but otherwise you just assume that it's a hydrogen. So since number 2 has 2 bonds, we know there's 2 hydrogens, the carbon needs 4 bonds.
Yes, so that's exactly right. Carbon is so predictable with its bonding that we know it's always going to have 4 bonds. Until a couple chapters where we see some weird stuff. But it pretty much always has 4 bonds. So that means that as long as we show the connections to non-hydrogen stuff, we can assume that the rest of the bonds are filled up by hydrogen. So we see carbon number 2 there is connected to 2 other carbons. So then we can say, oh, okay, then it must have 2 hydrogens because we got to get 4 overall. The ones on the ends, number 1 and number 4, same idea. That carbon is connected to 1 carbon that's shown, and so it must have 3 hydrogens to make up to 4. See how that works? 4? Okay. All right, so now that you know some more about that, you should be able to fill in the 5th column, or the 5th row, pentane, and see if you can go all the way across on that one. All right, hopefully you got something like this. Yeah, whatever you drew looks like an M or a W, maybe, for the bond line formula, or line angle formula. Yeah, great. It's always helpful with these structures, especially when they get big, to number the carbons like I did on the previous one, actually write the numbers on there, or just count to make sure. Because it's really easy, like if you're doing a chain of 10, it's really easy to go 1, 2, 3, and then you realize you forgot that first one is actually 1, and so you end up with one extra one. So just after you draw it, go back and always count the carbons and make sure you have the right number. Okay. So now that we've got a few of these, I'll just tell you that it continues. You can find the table in your book with all the names of all the alkanes as they get bigger and bigger and bigger. I'm going to ask in this class that we remember the names down to 10, which is called Decane. And so here's what I'm talking about. So now at this point, when we get to Decane, even the condensed formula starts to become tedious to write, right? We're going to write CH3 and then CH2, CH2 8 times, and then CH3 again. So we can actually abbreviate the condensed formulas in that way also, like this. We can say, all right, we've got a CH3, and then we've got 8 CH2s, and then another CH3. And that's going to be a lot easier than writing all those 8 CH2s out. The line structure, we can't really abbreviate, but it's pretty quick to draw a zigzag. So we can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we can recount that just to make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just to make sure we got them all. All right, great. All right, any questions so far? Okay, so our next task then is to talk about constitutional isomers. And so to do this, we're going to need some models. So we have some models for you to use here. We can do like one per table. Put together on this. And actually, we've got plenty of these. Oh, why don't we do one for each side? So I get a beautiful seed. Do you want another one, or are you okay there? You got room? If you'd rather just move around, that's fine. All right, guess our fire extinguisher is good. That was good. I was just going to start a fire. Okay. So after today, every time we're in here, if you could just grab these, because we'll be using them for the next few days. If you have your own models, if you want to get those out, you'll see over the next few days if that's something you want to have or not. They're great for if you have kids at home too. They like to play with them, especially if your kids are nerds like mine. Okay, so constitutional isomers are molecules with the same molecular formula and different connectivity. So I don't know if you noticed this, but once we got up to 4 carbons in our line here, and everything below that, there's actually different ways of putting those pieces together. So take your models out and build a butane molecule, if you would. So if you haven't used these models before, the little black, whatever the shape is, represent the carbon atoms, and you'll notice they have 4 holes in them at the correct tetrahedral angles. Some of the other ones do as well, some of the blue ones and stuff, that's fine too, blue, green, red, whatever. Just avoid the ones, I don't even have any here. Oh yeah, I do. No. Avoid the ones that look like bigger, because those have different angles in them. And so then you can just take some of these sticks. It doesn't matter which ones you use, but it works a little better if you take ones that are all the same size at least. But it depends a little bit on what's in your kit. And for now, let's ignore the hydrogen atoms as we did with our line angle structures. And let's just make some models of butane, or make a model of butane. Of just the 4 carbons connected together. So you should have something like that, which looks just like our line angle formulas, right? Okay, notice the open holes there. The remaining open holes on the black pieces represent the hydrogens that would be attached. So you should have 3 open holes on this one, and then 2, and then 2, and then 3. So if you were to add the hydrogens, you get CH3, CH2, CH2, CH3, right? All right, so now see if you can build an isomer of butane. Meaning, using the same pieces, can you make a structure that's connected in a different way? If you think you got one, hold it up. Okay, so we got a couple different possibilities. So a few people are raising this up. Is this or that? Does that represent a different connectivity? A different way of the atoms being connected to each other? Let's think about it. Do bonds rotate freely? Single bonds do rotate freely. So that means that this structure is actually the same, that however we rotate this, we still have the same structure. To find something with a different connectivity, we actually have to disconnect this and rebuild it in a different way, in a way that cannot be interchanged through simple rotation. So try to actually take some pieces apart and see if you can build a different structure from this one with these same pieces. Oops. So different connectivity is not bond rotation. Bond rotation gives you the same thing. Yeah, so I see a few of them around, right? They make a kind of triangle looking thing. So like this. So why is that different? How can we prove that that is a different connectivity from the previous structure? What? Count the holes. Yeah, exactly. So in this one, we no longer have CH3, CH2, CH2, CH3. We have a CH in the middle, and then 3 CH3s coming off that one. Right, see, 3 CH3s coming off that one. So let's draw those together in a couple different forms. So our original butane was this. And our new butane, our isomer of butane, is this. And so one name for this structure is isobutane. Then if we do that in a condensed structure, so we did this, right? CH3, CH2, CH2, CH3. The condensed structure for isobutane is a little bit trickier because it doesn't just follow a straight line. So we can't just write like CH3, CH3, and where do we put that third CH3? So there's a couple solutions to this. One is that you simply don't even try to write it in a line. And you write your condensed structure like this. So almost like a Lewis structure type setup. So you might see things like that. But sometimes it's really, really useful to be able to write things on one line, particularly when you're typing. If you're trying to type formulas into a whatever, word processor or something, it's actually pretty difficult to get lines to line up the way you want it. You really need a special program to do that. So if we can make this all on one line, that would be a lot easier. So there are a couple ways to do that. One is you write it kind of going across from right to left, and then when one of the things is coming off of something else, you use parentheses to show that it's coming off of the previous thing. So let's number these. 1, 2, 3, 4, we'll say. So then here that's 1, 2, 3, 4, and then here that's 1, 2, 3, and then this one is 4. You see that? So that's one way to do it. The other way to do it is to recognize that all of the 1, 4, and 3 are CH3s, and there's a CH in the middle. So sometimes you might see this written as that. So in this case, the CH is our carbon number 2, and then the CH3s are 1, 3, and 4. Yes, that's also okay. So CH and then 3 CH3s. Yeah. Oh no, I gotta plug it. How did that happen? I thought I just charged this. All right, I'll be right back. Takes a lot of battery to run this class. However you want. There's no correct way to number.
It would be on this plane 1, 2, 3, 4, 5, 6.
Yeah, the numbering only is to keep track of stuff. It's not about a correct or incorrect way of numbering it yet.
Okay.
We'll get to that later, but yeah. For now, the idea is just to keep track and find the different ones.
How do you dress
same, it's okay to draw.
So is it wrong if we put like the line in front, or is that?
No, it's not wrong. Generally, we want to expand the angle as much as possible so that we can approximate those 110-degree angles. So like when you draw it like that, it kind of looks like you have one big angle and then two little angles. So if you just kind of like stretch it out a little bit so that it's even, that's usually how it's done.
Okay.
But it's not, I wouldn't say it's wrong. All right, I see a lot of great structures around. If you could come draw what you've got up on the board so we can start taking a look at comparing them. Yeah. You can, or you can just use straight lines. Like you can just get like draw. So down to that one, but yeah.
Yeah.
I don't see any structures yet. Let's draw them. Let's draw them. You don't have to find them all. You don't have to find them all. Let's find them all as a class. So put up what you've got, and then let's see what we got. Wherever, yeah, wherever you have space.
She's so cute.
I'm sorry, so when we push, should we be different in other people groups, or should we just do all groups?
Let's say draw one or two per group, and try to draw ones that are different from the other ones. But if you're not sure, just put it up there. 7 on the board. So maybe I'm wrong, but I don't think I am. Does anybody have any other ones? Can we get even more? Is it no?
There's an O.
So should we call up the official chemistry whatever and tell them that we found some extra ones? I probably didn't say it.
Yes. We'll use phone in front and have you tell us which one.
Well, let's think about it. So this happens, right? You draw these things out, and because rotation doesn't count as isomerization, it can be really difficult to figure out if you've got the same thing or you've got something different. So can we think of any strategies of being able to do this, being able to compare structures so we're actually comparing things that are alike instead of just whatever? The one you just drew is the one with the W?
Yeah.
How'd you figure that out?
You just turn both.
Yeah, so one nice way to do this is by building the models. If you build it, then you can physically manipulate it, and you can stretch it out, and you can do whatever to make it the same. So that's great, and that's why we have the models. That can be really helpful. What if we don't have the models? So you can visualize it. Yeah.
Well, you can see it just based on like where the other connections are. Like you know the third carbon on that one has a connection, the third one on that one has a connection, and then the final one, the third carbon also has a connection.
Right, so I like that, the language that you're using about the numbers, like the third one, right? So we can talk about how these things are connected in relation to the other carbons. The way that we often do this for these structures is try to find the longest continuous chain of carbons and use that as kind of your basis for your numbering. So like for this one, we might say, okay, the longest chain of continuous carbons is right here. Can we see that? So we might number that 1, 2, 3, 4, 5. And then we can clearly see that the 6th one is coming off of the 3rd one. As you said. All right. So then when we compare that to here, remember we're looking for the longest continuous chain of carbons, not just whatever's horizontal. So we wouldn't go 1, 2, 3, 4. We would go 1, 2, 3, 4, 5, because that's a little bit longer to go that way. Everybody see that? That's the longest continuous chain. So if we do that, then once again, our 6th carbon is coming off of the 3rd. So let's say we wanted to evaluate that next to this one. Same idea. We could go 1, 2, 3, 4 as our longest chain. And then we can see 5 is coming off of 2, and 6 is coming off of 3. So clearly that's something different. If we go back over to this one, can you see this? Anyway, can everybody see this one? Sort of. Can you see that? You can see that. Let me redraw it over here. So it's this. Okay. So here we can see the 6th one is coming off of 4. Where we get into a little bit of a problem here is what if somebody drew this one? And then we went through this numbering thing and went 1, 2, 3, 4, 5. Oh, 6 is coming off of 2 versus 6 is coming off of 4. Those must be different. But those are not different right now. One's just the other one kind of flipped over and around. So we should probably stick to some kind of convention that's consistent, like let's always number from where the stuff is coming off. So the stuff that's coming off has the lowest possible number. See what I'm saying? So maybe we go right to left in this case, just so we're keeping the same rules all the way across. So now we can see, oh, okay, both of these are the same. 6 is coming off of 2.
But there isn't a hard rule.
Well, we're gonna get to the hard rule, but for now you can make up your own. Yeah. So using those kinds of ideas, those kinds of rules, we've now found that these two are the same. So that brings us down to, well, I read through this one, so let's get to that. So that brings us down to 1, 2, 3, 4, 5, 6. But we've still got one too many. Can anybody find an extra one? last one?
Yeah.
Let's take a look at it. So our longest chain is 1, 2, 3, 4, 5, and then the sixth one is coming off of number 3. So that's also the same as these other two, right? So now we've got 1, 2, 3, 4, 5. That's all. Question?
I do have a question for you. Why is the original one considered an isomer?
So isomers is a relationship. Two structures that have the same formula but different connectivity are called isomers of each other. So we don't say that this is hexane and these are the isomers of hexane. We say these are all isomers of hexane. These are all isomers of C6H14. Does that make sense? So it's a relationship between two
So like
structures.
in your other example where you had butane and isobutane, the other one could be considered isobutane?
Those are both,
as well?
well, those are both isomers of butane. It just so happens that that particular molecule is named isobutane. These don't have nice names like that. And we'll get into the more official ways of naming things. But yeah, isomers are relationships. So you can pick any of these, any two of these, like this one and this one, and say that these are isomers of each other, these are isomers of butane, including for these two, whatever. Any two structures that fit that definition are isomers of each other. Okay, so now that we're back online here, maybe? Yeah, go ahead.
So in the funky looking backwards K1, would you have to make the one arm like a triangle showing the angle or no?
You're talking about this one?
Yes.
Yeah, so a bunch of people ask this. So when we draw a structure like this, where you've got multiple things coming off of the same carbon, how do we draw that? And there's two correct answers. So one is that you can show the three-dimensionality of that. So you could show this as a wedge and a dash, like that. That would be fine. But it's also okay to just draw the lines like this. In this case. In a couple chapters, we'll see where when these things are different, it actually matters which one's forward and which one's back. And usually the convention is to draw this only when it really matters, when it's important to show this is forward or back, because that's actually a different structure. When it's all the same and it doesn't matter, then this is okay. All right, so we've got those isomers. While you're working through your homework with this stuff, please practice drawing these types of structures. I will put some extra practice on Blackboard as well, because I feel like this book doesn't have a whole lot of practice for that particular skill. So I have some other stuff too that I like to use with that. But we're going to try to practice that, because this is the predominant way that we will communicate structural chemistry throughout the rest of the semester. So this is how we'll be drawing our structures generally. We won't really draw the typical Lewis structures with all the stuff coming off much anymore. All right. So the next step, which we won't completely finish up today, but we'll get started with, is naming. We use a system of naming for organic chemistry that comes from the International Union of Pure and Applied Chemistry, which is the same group that you might remember coming up with those names in general chemistry, the like numbers in parentheses and having the different types of naming for inorganic compounds. We have naming rules also for organic compounds, because much like with the inorganic compounds, it's really difficult if every single structure that you could draw has a different name. And there's no way of knowing that except to memorize all the names. So it's a lot easier, even though it's going to seem a little tricky at first, it's a lot easier if we have rules for naming, and we just follow the rules, and we get an unambiguous name that anybody else who knows the rules can decode back into a structure. So let's take a look at the way that we name that we name organic molecules. Okay, so we're going to talk about 3 parts of a name, and I'll try to use different colors here and keep it straight. Our name starts with what we call the parent structure. Before the parent structure, we have a prefix, and after the parent structure, we have an end or a suffix, which is the functional group, or which represents the functional group. Let's define these, and then we'll practice them, and hopefully it'll make a little bit more sense. The parent group is going to be generally the what we did before, the longest. Sorry, suddenly the computer is being very slow here. The longest continuous carbon chain. And the prefix is other stuff attached to the chain. So you can kind of see how that's going to work in some of our structures that we've drawn up here. Our longest continuous chain is going to form the parent name, the main part of the name. And then our prefix is going to be whatever stuff is coming off of that parent chain. So let's look at how that works. The names for the parent are the ones that we've already learned. They're going to be those words that we used for the different names going up to as big as we need to go to. In our case, 10 will suffice for this class. So meth, eth, prop, but, whatever. Pent, hex, hept, oct. You can look in the book for all those names. Those are just things you have to remember. Those are just a memorizing thing. And then the functional group is, we haven't learned about a bunch of different functional groups. So right now, our functional group is always going to be ane for alkanes. Okay. So the middle and the end part of the name for us right now is always going to be those same words that we've just been using: methane, ethane, propane, butane, pentane, hexane, so on. Our other stuff attached to the chain is going to be a little bit trickier. So it's going to add YL, but I think it makes more sense to look at this in some examples rather than just write down a bunch of rules that don't make a whole lot of sense. So let's take a look at some of these structures and talk about how we would write their names in this format. All right, let's start with this one that gave everybody so much trouble. It was so important we had to draw it 3 times. Let's say that way. So when we try to come up with a name for this structure, the first thing we want to do is find the parent. Find the longest continuous carbon chain. And then we're going to number it just as we did on the board. So 1, 2, 3, 4, 5. Since this chain doesn't have any other functional groups, that already gives us the last 2/3 of the name, which is down here. Pent, because it's got 5 carbons in the main chain. The main, not the whole structure, but just the parent chain. And then we can also add our suffix, which is going to be ane, because it's an alkane. Other functional groups will have different suffixes. We'll get to those on Monday. Okay, so now it's time for our prefixes, which is the stuff that's hanging off here. So what's hanging off of this chain? What's hanging off of the parent chain here? How many carbons? How many carbon groups? Just one group, right? And that group just has one carbon in it. So we would say we would need to know how many carbons are in the group and where is it on the chain. So which carbon is it on the chain? It's on the third carbon. A one carbon group is called a methyl group. So let's meth for one carbon with YL. So our prefix becomes 3-methyl. And it's all one word. The words are all just smashed together. So the name of this molecule is 3-methylpentane. We use dashes to separate numbers and letters, or hyphens to separate numbers and letters. So 3-methylpentane would be the correct name of that structure. Yes?
What 3? Just because it's connected to the third one?
Yes, exactly, because it's connected to carbon number 3.
So it's connected to the fourth one and say 4 now.
Right. So let's take a look at that. So a similar structure that we drew up on the board is this one. Okay? Same idea. The first thing we want to find is our parent chain, which again is pentane with 5 carbons. But this time, we want to be a little bit more careful about our numbering so that we don't get into trouble the way that we did over here with two structures that have different numbering schemes. So we're always going to number the chain so that the substituents, the things that are coming off, have the lowest possible number. So that means in this structure, we number from right to left instead of left to right. This word that you may not have heard before, substituents, means things that are substituting for hydrogen, so things that are coming off the chain. That's the other stuff that's coming off the chain. So this way, our substituent, our methyl group that's coming off of the chain, can be on number 2, whereas if we numbered it the other way, it would be on number 4. So we always want to have that have the lowest possible number. So then this becomes two methyl pentane. See that? So now we have a unique way of talking about both structures. Okay, let's try another one. What happens if you have multiple substituents? So let's take this one. How many carbons in the parent chain for this one? 4. There is 4. That's the longest continuous chain. Does it matter if we number from left to right or right to left or up to down or down to up or whatever? In this case, it doesn't because it's all pretty symmetrical. So we can start the numbering wherever we want as long as it's at one of the ends. We can go 1, 2, 3, 4. We could make our 4 the one down there. We could do that however. It doesn't matter for this structure. All right, so this one, that means that our parent name and our suffix, instead of pentane, are going to be, I'm going to give myself a little more room with the prefixes here. So this is going to be a butane structure instead of a pentane structure. Right? Because we've got 4 carbons in the longest continuous chain instead of 5. And then this time we have 2 methyl substituents, one on carbon number 2 and one on carbon number 3. So the way that we write that is 2,3 dimethyl butane. So we don't say 2-methyl, 3-methyl, because if you imagine that if it gets a pretty big structure, there's a lot of methyls on there, it's going to start really expanding that name. So we can make that a little bit easier to understand by just saying 2,3 dimethyl. The di tells us that there's 2 of them, and then the 2 and the 3 tell us they're coming off of each carbon. So notice the punctuation there. We use a comma to separate the numbers, and we use a dash in between the numbers and the words. All right, so how do you think this structure then would be named? Let's see if we can come up with a name for this one in our last 2 minutes. Take a look at it and see what's going to try. Yeah.
I have a question.
Oh, yeah.
How come then in the first, the butane, how come the second one was only called isobutane?
Yeah, good question. So we had, actually, so forget about that for a second. Let's go back up to that one. We called this one isobutane, but that doesn't really follow the rules, right? And that's true. Isobutane is what we call a common name, a name that doesn't follow the rules, that it's just called that. You don't have to know that it's called that, because we're going to focus on the systematic names, the rule names in this class. So how would you call that structure using our rules instead of isobutane? 2-methyl propane. Yeah, 2-methyl propane, because it's got a 3-carbon chain with a methyl coming off of number 2. So the better name for that structure is 2-methyl propane. However, chemistry's been around a long time, way before these rules were made up. So small molecules, common molecules, are often called by their common names. So ones that we use all the time. Every once in a while, I'll tell you, okay, you need to know this name, but most of them, we don't need to know the common names. Where that comes up is stuff like in lab. So we take something like acetone that we wash our glassware with. Acetone is a common name. It doesn't follow any of the rules. There's no acet for one of the parent names. But it's this thing that we've used forever, and we just call it acetone. So that's how isobutane works too. It's a common name, but it's not really the best name. All right, so it's 10:45. We'll stop there, and we'll continue with this on Monday. Please start practicing this stuff. All these rules, all of this is in the book. So start working on the homework so that you're not kind of stuck when it comes to next week. Yes, Nicole. The test will be through probably chapter 4, maybe not the entirety of chapter 4. It depends on how far we get next week. Not chapter 2, right? Yeah. So 1, 3, and part of 4, or all of 4, depending on